Hi everyone, and welcome to lesson 2.4, which is hypothesis test for population proportions. In the last lesson, we learned about hypothesis tests, and we concluded that if the null hypothesis was true, sample proportions that fell more than 2 standard errors away from the mean were considered unusual, and therefore the null hypothesis should be rejected in that case. So, what does unusual actually mean? We're going to look at another way to determine whether we should reject the null hypothesis or the claim that's being made. So if you'll recall the problem from 2.3, an online store advertises that 80% of all the orders received are shipped within 2 days. A consumer group is interested in testing this claim. They think it is lower than 80%. The group takes a random sample of 60 orders out of all of the orders that were processed last month. And in this sample of 60, they found that 40 were shipped within 2 days. So our null hypothesis, remember, is our status quo. So it is the actual claim. It's always going to be an equals. And in this case, we're dealing with P, which is our population parameter. And we're saying, the null is saying that the proportion of orders received that are shipped within 2 days is actually 80%. Okay. A consumer group, however, thinks it's lower. So they would be the alternative, which says the proportion is actually less than 0.80. We looked at a sketch. So we drew the normal model. And we know it's normal because it passed the 3 conditions. So remember, those 3 conditions are that it has to be random, the 10% rule, and also the success failure rule. So here's our claim right in the center because that is our average or mean. We calculated the standard deviation and we listed 2 standard errors in either direction. And our sample proportion, which is 0.67, which comes from our sample, which says that out of 60 orders, 40 were shipped within 2 days. So if you change that to a decimal, you get 0.67. So right there, that would be basically where my red flag is. Okay, 0.67, that's my p-hat. And we're looking for the probability that it's less than that. Okay, and because our sample proportion was 2 standard deviations below, more than 2 standard deviations below the average, we said that this was unusual, and also then the null hypothesis should be rejected. Okay, but why? So we're going to take a look at that. So we want to find the probability that we would find a sample like this or smaller if the company's claim is true. So what we're testing against is the null hypothesis. So to find our z-score or z-value, we know that normally z is just equal to the value minus the mean, and then divided by the standard deviation. Okay, and this formula is going to, we're going to tweak it a little bit each time. So our value here is just our sample. It's our p-hat or our red flag. And we're going to subtract the mean, which in this case is p, and we're going to divide by the standard error. So here we have 0.67 minus 0.80. And then we determined that our standard error comes out to be 0.0516. And the formula that I'm using for that is p times 1 minus p over n, if you'll recall, and then take the square root. So that's where that number 0.0516 is coming from. And we end up getting for our z-score negative 2.5194. So as you can see, it's more than the p-hat, our sample proportion, is more than 2 standard deviations below average, which tells us that it's unusual. But if I want to find the probability that we would find a sample like this or smaller, I'm looking for the shaded region to the left of the red flag. So I need to do the normal CDF. So the probability that z will be less than negative 2.5194 is just normal CDF. My lower bound, remember, is really negative infinity. But if we use negative 100, that'll suffice. And then we know that z for our p hat is negative 2.52, basically. So that's going to be my upper. And then my mean is 0, my standard deviation is 1. And when I do that, you end up with 0.0062. So what is the probability that we would find a sample like this or smaller if the company's claim is true? And if the company's claim is true, the probability is 0.62% of getting a random sample of 60 orders with 67% or less shipped on time. So if our claim was true, there's less than 1% chance of getting a random sample of 60 orders with 67% or less shipped on time. In other words, there's a 0.62% chance of getting a random sample like this or less if the company's claim is true. Less than 1%, right? So if someone told you the chances of this happening are less than 1%, that means it's very rare or unusual, right? Which isn't surprising because we found our z-score to be negative 2.5. It was more than 2 standard deviations below average. So it's unusual, okay? What we just found is what's called the p-value. And this is going to be really, really helpful as we're doing hypothesis tests. So the p-value is the probability of finding a random sample like this, or more extreme, if the null hypothesis were true. So because it's such a low probability, we're basically saying we're rejecting the null hypothesis. The chances of it being true are so slim. So how small is small? What we use is what's called a significance level. That will help us determine whether the probability that we got, or the p-value, is actually small. So the significance level is the Greek letter alpha. And if the p-value is less than alpha, so if p is less than alpha, we're going to reject the null, okay? If the p-value is greater than alpha, we're going to fail to reject the null, okay? In other words, fail to reject means do not reject. Our alpha level usually is 5%, or 0.05. Sometimes if we want to require stronger evidence, we would use 1%. So your alpha level should become smaller the stronger the evidence that you want, okay? For example, if you are testing the wings on a plane, and you're trying to do some statistical analysis, you wouldn't want your alpha level to be high, like 5% or 10%, because if you test a different wings and you're trying to figure out, okay, will these wings actually fly in the sky, or is the wing going to fall out? You would want your alpha level to be low, so even lower than 1%, because you want to really be sure that these wings are going to be to have quality and they're able to keep the plane in the sky. So it depends on what it is you're trying to test. So a couple things you need to know. A small p-value means reject the null hypothesis, right? And how small, we're going to look at the alpha level. So if p is less than alpha, we reject. If the p-value is less than the significance level, alpha, it's considered strong evidence against the null hypothesis. And basically you're saying you're for the alternative. Okay. So here's the 4 steps for doing hypothesis tests. Step 1 is you always want to Write the null and the alternative hypotheses in symbols and words. The null, for your sake, is always going to be the equal sign, and we're always interested in the population, so we're going to have p. Okay, and for our alternative, we have three options. Either it's going to be less than, greater than, or not equal to. Less than and greater than are called a single-tailed test. So less than, you shade on the left. It's called a left-tailed test. Right is right-tailed. And then not equal to is called a two-tailed test. Step number 2 is you want to examine the data. Okay, so the 3 steps. Was it random? My 10% rule, is it reasonable to assume that the population is greater than 10 times the sample size, or 10n? And then my success failure, is the sample size large enough to use the normal curve? So we have to confirm that n times p and n times 1 minus p are both greater than or equal to 10. Step number 3 is assess the evidence. Okay, so you're always going to sketch the sampling distribution of p hat. You want to mark p hat on the sketch and shade into the tail in the direction of the alternative hypothesis. If it's a two-tailed test, you're going to shade both tails. And you can see in the pictures below. And then you want to find the z-value for the sample, then use normal CDF on your calculator to find the p-value. Okay, so left-tailed would look like this. Here's p, and here is your p hat. We're shading to the left, so that's your p-value. And here we have right-tailed, so there's your p hat, and we're shading to the right. And then here we have p is not equal to for our alternative, so that's called a two-tailed test, and you shade on either side. And then step number 4, which is very important actually, is state the conclusion in context. Okay, so you're telling me I am either rejecting or failing to reject the null. So if the p-value is small, remember we reject, okay? And that gave us strong evidence against the null and in favor of the alternative. If the p-value is not very small, so if it's larger than alpha, we decide that the null hypothesis can't be ruled out. So remember, we fail to reject, or we say we do not reject. This is not considered evidence for the truth of the null hypothesis. Okay, so that's important to remember. It's kind of like, when someone is on trial, we know that they're innocent until proven guilty. Okay, the null would say that they're innocent, and then the alternative would say that they're guilty, okay, or they're not innocent. When you gather evidence, you don't ever say that the person is innocent. You just basically say that they are not guilty. So you don't have enough evidence to suggest that they are guilty at the time. Okay, let's take a look at the example here. So this is called the bottled water challenge. A friend says that he conducted informal research and he estimates that 70% of teenagers preferred bottled water to tap water. You find this estimate to be low and you decide to test your friend's hypothesis. So you randomly select or sample 50 teenagers. You find that 45 prefer bottled water. At the 5% level of significance, what can you conclude? Okay. So step 1 is to determine the hypotheses. We're going to write the null and the alternative. Okay. Remember, the null and the alternative both use p because we're always interested in the population parameter. But the null, you only have one choice. It's got to be equal. Okay. And here it's equal to the claim, and the claim is the 70%. Okay, you find the estimate to be low. So what would you think the alternative would be? Okay, so if you find it to be low, you think it's actually greater than 0.70. So in words, my null is the proportion of all teens who prefer bottled water to tap is 0.70. And for the alternative, it would be the proportion of all teens who prefer bottled water to tap water is more than or greater than 0.70. And again, notice I'm using the word all because I'm dealing with P, and P is the population proportion, which means all. So in order to conduct my hypothesis test, I need to check the assumptions and make sure that I can use the normal model, okay? So are the conditions for approximate normality met? So the first thing I need to do is check for randomness, okay? Does it say anything about random in the problem? And it does. It says randomly sampled 50 teenagers. So we have a random sample of 50 teenagers. Okay, next I want to check the 10% rule. So I'm going to take 10, multiply it by my sample size, which is 50, and I get 500. And just ask yourself, is it reasonable to assume that there's more than 500 teens in the world? And that is yes. Okay, and then I'm checking my success failure. So that's going to be n times p, and p here, you just go back to your hypotheses, is 0.70, and 70% of 50 is 35, which is greater than or equal to 10. And then you can do 50 times 1 minus 0.70, or 50 times 0.30, okay, or just take 50 minus 35 and you get 15, which is also greater than or equal to 10. So yes, the conditions for approximate normality are satisfied. So we're ready to move on, and we're going to apply what we know about the normal model. So we're going to calculate the sample proportion, okay, my p hat. So it told me in the problem that we randomly sampled 50 teenagers and 45 preferred bottled water. So my p hat is going to be 45 divided by 50, which comes out to 0.90. Now we're going to assess the evidence. So we're going to calculate the mean and the standard error of the sampling distribution. So remember, my mean of p hat is just p, which is 0.70. It's my claim. And the standard error is equal to the square root of p times 1 minus p over n. And I'm just going to calculate that out, and you would get 0.0648. Okay, I'm going to use that information now to draw the sampling distribution. So we're, again, assuming normality. So we know 0.70 is going to be our center. And we're going to go 2 standard deviations in either direction. Okay, so what I'm going to do is add 0.70 plus 0.0648. Okay, and again, when you're making the curve, you can just round to 2 places because it gets kind of busy if you don't. And then add another 0.0648. Okay, and then I'm going to go backwards and subtract 0.0648. and I'm going to place my p hat here. P hat is 0.90. Okay, so I need to figure out how many standard deviations away from the mean that would be. So I need to calculate the z-score. And when you do this, you should end up with 3.0864. So it's more than 3 standard deviations away from the mean. So you can predict now, would you end up rejecting the null or not rejecting the null? Okay, if you said rejecting, you're correct. It's because it's more than 2 standard deviations away from the mean. And it is very unusual that you would see a sample proportion of that size or more extreme. Okay, so judging from the z-value, is our test statistic unusual? And the answer is yes, it's more than 2 standard errors away from the mean. Okay, we're going to use the test statistic to determine the shaded area. So what we're doing is we're finding the probability that z this time is going to be greater than 3.0864. So why greater than? Because I always go back and look at the alternative hypothesis, which uses greater than. So we're shading to the right. And we know that z is 3.0864. Okay, so that's not scaled correctly. Obviously, it should be moved down a little bit to a little bit more than where 3 standard errors would be, but you get the idea. Okay, now I'm going to do normal CDF. And this time my lower bound is going to be the 3.0864. My upper bound is going to be 100. And then the 0 and the 1 we're not changing, right? So here's my lower bound, 3.0864. My upper bound is positive infinity, but I can't put that, so we use 100. And then 0 and 1. And when you do that, you end up with so if I change that to a percentage, if I move this decimal 2 places to the right, you actually get basically 0. It's 0.0967%. Okay, so what does that tell me? Okay, using the p-value and the level of significance. So it told me in the problem that my significance level was 5%. That's telling me that alpha is 0.05. So we're going to look and see, is our p-value greater than that or less than that? And 0.05, so you've got 0.000967, right? So if I look at this number here, is less than 0.05. So that tells me I'm going to reject the null. It's saying, okay, there's not enough evidence to suggest the claim being made is true. So we're rejecting the null because, again, this is your p-value. And if you go back and look, the p-value by definition is the probability of finding a random sample like this or more extreme if the null were true. So the probability is so low that more than likely the null is not true. We gathered our evidence and proved that. Okay, so using the p-value, will we reject? As we said, we're going to reject the null. So basically we would say this, since p equals 0.000 967 is less than my alpha level, I reject the null. And then we're going to interpret our decision. Okay, this is one way you can word it. So since the p-value was small, there is enough evidence to conclude that more than 70% of randomly sampled teens prefer bottled water. My p-value was 0.0009, pretty much. So another way that I like to word this is you can say there is strong evidence to suggest that the proportion of all teens who prefer bottled water to tap water is greater than 0.7. And this should sound familiar to you because this part right here is the alternative. So we always write our conclusion in terms of the alternative. We're basing our rejection on our p-value, which is related to our p-hat. And the p-value will tell you whether you're going to reject or not reject the null. If the p-value is less than your alpha level, you reject the null. And you say there's strong evidence to suggest. And then you mention your alternative hypothesis. If your p-value is greater than the alpha level, then you don't reject the null. And then you would say there is little evidence to suggest. And then you mention the alternative hypothesis. You can feel free to try the next problem on your own. This one will be a two-tailed test, so be careful when doing this. You can always use the resource videos that I've placed in Canvas if you need some help with two-tailed tests to kind of guide you through this. And if you have any questions, feel free to reach out to me. Have a mean of 35 and a standard deviation of 5. So remember that this is actually mu and this is sigma. Okay, mu is, again, the population average or population mean. Okay, so you're taking into account all these cars whose speed was taken. So that's your population. And then we found the standard deviation as well. It was given to us in this problem. This is our population standard deviation of 5 miles per hour. Okay, so we know that the mean goes in the middle because it's the average. So 35 is going to go in the middle. And since my standard deviation is 5, I'm going to add 5 to 35 and I would get 40. And that represents one standard deviation above the mean. Okay, 35 minus 5 is 30. That would be one standard deviation below, and so on. Okay, I'm going to go back to the mean. 35 plus 5 gives us 40. 40 plus 5 is 45. 45 plus 5 is 50. So this is 2 standard deviations, 3 standard deviations. And if I go backwards, I'm just going to subtract 5 each time. So we know that this 25 miles per hour is 2 standard deviations below, and 20 miles per hour is 3 standard deviations below. So there's my normal distribution set up according to this problem. And by looking at it, I know that my mean is 35 And these are your z-scores. If you're a car that's traveling 40 miles per hour, right, you are 1 standard deviation above the average speed. Okay, so these represent the z-scores. Okay, so that would just mean z equals 1, and this means z equals -1. So if you're a car and you're traveling 30 miles per hour, you're actually 1 standard deviation below the average speed of the cars on that road. So then answering these questions, what is the probability that a randomly selected car on this road is traveling below 25 miles per hour? So think of this right here is our 25, and I'm going to put a little flag right here. We want the probability that any car randomly selected, right? So any car would have an equal chance of being chosen, that car is traveling below 25 miles per hour. So I need to use my empirical rule to figure that out. So if you'll recall, anywhere from 25 to 45 is 2 standard deviations above and below the mean. And using the empirical rule, we know that that area in between the two flags is 95%. So if I take 100% and subtract that 95%, it's going to leave me with this area and this area. So in other words, if I do 100 minus 95, I'm really subtracting away this piece right in here. So it's going to leave me with 5%, right? But that represents either side of the flag. We only care about this side. So I need to divide by 2 because remember, one of the properties of the normal distribution is that it's symmetric. It's the same on both sides. So these flags are the same distance from the center. So I'm just going to do 100% minus 95%, which gives me 5%. And then I'm going to have to make sure I take the 5 and divide by 2, which is 2.5%. So the probability that a randomly selected car is traveling below 25 miles per hour is actually just 2.5%. Now I want to know, what is the probability that a randomly selected car on this road is traveling between 35 and 40 miles per hour? Okay, so I'm going to take this this picture here, and I'm just going to copy paste. Okay, I'm going to shrink it down, and I'm going to, let's see if this will work. Let me put that back a second. Let's see. Okay, instead of redrawing, I can just go like this, and then maybe I can erase that stuff. Okay, so I'll do the best I can getting rid of this stuff. All right, I don't want to mess with it too much, but hopefully you can all see now. So now I'm looking for 35 and 40 and in between, right? So let me use a different color here. So 35 is here and 40 is here. And there's a couple ways you could do this, okay? So one way that stands out is, if you'll remember, between here and the furthest orange flag, so here, that's 68% of the data. It falls within 1 standard deviation. But I'm only looking for the probability that someone traveling on that road is going between 35 and 40 miles per hour. So using one of the characteristics of the normal model, I know that it's symmetric. So all I would have to do is divide this 68 by 2, because this area is the same as that area. And 68 divided by 2 is 34. So approximately 34% of cars traveling on that road will be traveling between 35 and 40 miles per hour. Okay, we know that the middle 95% of cars are going to be 2 standard deviations above and below the mean. So we know they're going to be between 25 and 45 miles per hour. And almost all of the cars on this road would be traveling between 20 and 50 miles per hour. Anything beyond those two values is extremely rare. In this book, we say anything above 2 standard deviations is rare. So the probability that someone is driving more than 45 miles per hour on that road would be rare. And the probability that someone is traveling less than 25 miles per hour would be rare. So if you think about it, anybody going above 50 or below 20 would be extremely rare. So mostly everybody, 99.7%, are traveling between 20 miles per hour and 50 miles per hour. The reason we can't say 100% is because, remember, the whole curve represents 100%. So that's the end of this lesson. We're going to see more of the normal distribution throughout the entire book. So it's really important, this section, that you understand z-scores and also the normal distribution. So please go back over the notes and go over the summary here. These are highlighting the important things that you need to know. And then there's the homework at the end. This is the bare minimum of practice that you should do to feel comfortable with this section. If you need more practice, I can provide more problems for you to try. But doing these problems is, again, the bare minimum. If you've never seen this before and you need practice doing it, because a lot of what we're going to do going forward will relate to z-scores and the normal distribution, and your understanding of it is critical to understanding the rest of the course. So please reach out to me if you have any questions, and I hope you all enjoy the rest of your day.